Algebra 285, exponential and logarithmic equations. Before we get to example 1, I want to introduce a change of base theorem to you. Many times we run into base logarithms that we cannot calculate. There are two bases which are programmed into every scientific calculator. That would be base 10 and base E. We'll talk about base E later. For now, we'll just be dealing with base 10. So you can take your calculator and you can find, like there's a button that says log, that's base 10. So log of 5. You can take the logarithm of 5. In other words, you're going to find the exponent on 10, which gets you 5. So there's a weird decimal. Not something you need to know or have memorized or anything like that, because nobody would know that. Well, so you can do that for any logarithm as long as it's base 10. Most of our logarithms are not base 10, so we have a way to change them to base 10, and that's this change of base theorem. The change of base theorem says that you can take the log of the argument over the log of the old base. And according to this theorem, you get to pick whatever base you want. You pick the new base, and we will most commonly be referring to base 10 or base E. But as I said a few minutes ago, we'll discuss this option of using base E later, so I wouldn't worry too much about that right now. But understand this theorem. The log, see, here's your argument, and here's your old base. And we could take the logarithm of the argument and divide the whole thing by the logarithm of the old base. And like I said, you get to pick the base that you want. We are many times going to be choosing base 10. Sometimes it's useful to choose base E. So let's look at example 1. Now, I am not going to use the method that the book uses. So if you ignore me or don't take these video notes, you're going to find people sitting at your table that are going to try to read the book. The book's method is okay. It's fine. But I think that there's a little bit of an advantage to doing it this way. When I see something that I know that I cannot raise to a common base, so I know I can't rewrite 20 as a power of 7. That just isn't going to work. What I want to do is change it to its log form. So if we change it to log form, what we get is log base 7 of 20, right? 7 of 20 equals 3x. Seems simple enough. Now, here's where I can't use my calculator at the moment because I don't have a calculator that does base 7 logarithms. But if we use that change of base theorem, we can take the log of the argument and divide by the log of the old base. And now, look, I've changed it to base 10. I got to pick the base, and I picked base 10. So let's see here. Log 20, n parenthesis, that n parenthesis is extremely important. Make sure that you are putting that in there. Otherwise, you will get the wrong answer. Divided by log 7. I get 1.54. It's going to be an approximate value. 1.54 is approximately equal to 3x. Shouldn't be that hard to figure out that you need to divide by 3. get your final answer. So, x equals 0.51, approximately 0.513. Now, I have the ugly looking number in my calculator, right there. Right now, this number right here is stored in my calculator as the last answer. I'm going to check it to make sure that it's right. 7 to the parenthesis 3 answer. Answer button is above the negative sign, so look for that and use it. Now this should be 20 if I've done everything right, and it is, so I know I did it right. Okay, try again. Change it to its log form. Log base 3 of 4 equals x. My calculator won't do base 3, so I change it to base 10, log of the argument over log of the old base. Seems pretty straightforward and easy, so let's check it. Make sure it's right. Log 4 parenthesis divided by log 3 parenthesis gives me about 1.262. Always double check it to make sure it's right. So 3 to the answer power, and this better be equal to 4 according to the original equation, and sure enough it is, right? The original equation was 3 to the x equals 4. Okay, we can try again. Now, log base 6 of 21 equals 2x. Now, just to kind of conserve space, I'm going to show you what I do. I'm going to put another equal sign on this side, and I'm going to take this logarithm right here, and I'm going to change the base. Log 21, log of the argument, over log of the old base. So now, instead of this equation, I'm really dealing with this equation. All I did was I changed the other side by using the change of base theorem. Well, all of us should know how to cross multiply. That's all you're doing here is really cross multiplying. So, what do I have here? 2 log 6 in parentheses divided by log 21. There we go. 1.177. Let's just double check my answer to make sure I'm right. Here, I'll write it down. X equals 1 is approximately equal to 1.177. Let's just double check my answer. 6 raised to the parenthesis 2 answer power. Now, if I'm right, then I should have 21 according to this. Uh-oh. Something happened. What'd we do wrong? Let's check it out, see what we did. Make sure I typed it in right. Log 21. Let me type my answer in again just to see if I did something wrong. 2 log 6 in parentheses equals that divided by log 21. Okay. 6 caret 2. Keep in mind, whenever you're doing something and you make a mistake and you've plugged it back in, you're double checking it and you're like, man, this is wrong. Look at it again and see what you did, right? Because really, 2x times log 6 should be equal to log 21 times 1. We weren't wrong in saying cross multiplication should work, but we should maybe be careful how we do it. So even if we make a mistake, my answer of 1.177 was the reciprocal of what I wanted. So I made a mistake. You will do the same. So all you have to do is, now I don't know if you recognize this trick, but anything raised to the negative 1 power will flip the base. So now I have the correct answer, right? If I took my answer before and had done this, I would have gotten the correct answer. And now when I do the 6 caret parenthesis 2 answer, I will get 21. So log 21 divided by parenthesis 2 log 6 will give me the correct answer, 0.85 approximately. So x equals, or is approximately equal to 0.85. Always check your answer by plugging it back in. Otherwise, you'll accidentally choose the wrong value thinking maybe you did it right. So, excellent way to check your work is to plug it back in. All right, we'll try it again. All right, log base 3 of 101, right? 3 of 101 equals x plus 4. Okay, so switching this to the other side, we know that this is log base 10 of 101 over log base 10 of 3. Now another way to handle this is just to realize this is a number, right? In fact, some of you might think that's a lot easier to do. I'm just going to do it that way. As long as you put this extra parenthesis in right here, you will be fine. Now, in this case, I'm going to get 4.2. So x plus 4 equals, or is approximately equal to 4.2. Then I can just subtract my 4 to the other side, so x is approximately equal to 0.2. The more technical version looks like that, right? Double check your work. 3 caret parenthesis answer plus 4 end parenthesis gives you 101. So we were correct. Now, keep in mind, they have quite a few examples in here which rely on a graphing calculator. We are skipping example 2, 4, and 5 because they are heavily involved in the graphing calculator, and that's not really what we're going to emphasize in this class. So don't worry about those. Example 3 is a duplicate of example 1, so we're not going to worry about that one as well. I should say example 2 really isn't about a graphing calculator, but it's changing a base into another base, and I'm not really sure I understand the purpose of that. We changed the base in order to get it into base 10 so we can use our calculator and solve, but I'm not really sure there's a point into changing it into some other base that's not useful. So we won't be doing example 2. Example 6, solving logarithm equations. Okay, so here's an example of solving a log function. First of all, you have to have a single logarithm. So I need to check, is it a single logarithm? If I'm convinced that it's a single logarithm, then I can rewrite it into its exponential form, because some of these questions you need to change to its log form, and some of them you need to change to their exponential form. You can't have it in both. You need to pick one that's going to be helpful to you. So 10 to the 5th power, right? 10 is the base, 5 is the exponent, equals 3x plus 1. Now 10 to the 5th, isn't that a 1 with 5 zeros? So that's 100,000 equals 3x plus 1. Subtracting 1 and dividing by 3 gives me 33,333. So, and you can always check your answer. Log 3 times 33,333 plus 1. This better equal 5. And it does. So, always plug back in. It doesn't take that long to actually check your work to make sure it is correct. Okay? We'll try another one here. Make sure it's a single logarithm. If it is a single logarithm, then you have the green light to go ahead and switch it to its exponential form. 10 to the negative first equals 7 minus 2x. We know that 10 to the negative first is equal to 0.1. So we will be subtracting a 7, getting negative 6.9 equals negative 2x, and dividing by negative 2. So 3.45, x equals 3.45. And of course we can always go back and plug it in. I've done enough checking, but I encourage you to make sure you plug it back in. I can do it real quickly. Probably should do it real quickly instead of just saying something to you about it. Log 7 minus 2 answer. And should be equal to negative 1. If it is, I'm good to go. These clearly are not in single log form, so it's time for me to change them into single log form. Using my properties, we know that we're going to move this up and make it an exponent. So it's log x squared minus log 3 equals 2. We see that we have subtraction, so we're going to put these two things together into a fraction, right? Whenever we are subtracting, this is just like, remember we've talked about how logarithms are exponents. So if you're subtracting two exponents, that must mean you were dividing. Whenever you divide like bases, you subtract exponents. That's what it makes me think of. Now that we've got it as a single logarithm, we can change it to its exponential form. So we have 10 to the second power equals x squared over 3. So if we multiply by 3 on both sides, 3 times 100, that's what 10 squared is. We've got 300 equals x squared. And so then we can get the approximate decimal value by taking the square root of 300, and the square root of 300 is going to be 17.321. You can always go back and double check and type the original equation back in using answer for the x values. 2 log answer minus log 3, and you better end up with a 2 if you're going to have the right answer. So, works out great. Try another one. Remember, we're trying to get things into single log form before we do anything else. So I see subtraction. That must mean I'm going to put these two arguments together by dividing them. Now, can you reduce that or simplify that? Sure you can. We could change that to log 2 over x equals negative 2. And then, since it's a single logarithm, we can change it into its exponential form. 10 to the negative second equals 2 over x. Sure looks like a proportion to me. In fact, we could change it, and 10 to the negative second is 1 over 100 equals 2 over x. We could cross multiply this, right? 1 times x equals 2 times 100. And once again, we can go back and check our work. Log 6, n parenthesis minus log 3 times 200 n parenthesis should be equal to negative 2, and we do have a correct answer. All right. Quick question. Since we took a square root back here on the previous question, should I have a plus and a minus? Should I have a plus and a minus? Well, think about it. If you had a negative value for x, go back to your original equation. What's the logarithm of a negative number? Oh yeah, that's the one we said has no solution. So in all reality, that one wouldn't even count. So don't think that you need to have a negative on that, because when I go back and plug it back in, it wouldn't work. So no negative needed. Okay,